All right, so let's take a look at the questions I assigned from section 1.3. So we want to plot a slope field or direction field, vector field, all equivalent names for the same thing. From this differential equation over these values of t and x. So first let's draw our plot. So I won't care about going from -2 to 2 on both axes. And the point of a slope field, especially when you draw them by hand, is not to, it's less about accuracy and more about visualizing how these differential equations respond depending on whatever initial conditions you give. So let's handle just any integer value of t and x here. We can start with the origin. At 0, 0, we're going to have a slope of 1. And let's think about what happens if I stay on the y-axis. Or really, let's mark these axes. This is x, this is t. What happens if I increase x? If I increase x, then my slope is going to, let's really make sure that it's increasing. It's going to go to 2, then go to 3. What happens if I go down the y-axis? Then my slope is going to go to 0, then -1. And the way I'm handling this is just a personal preference kind of thing. I like to kind of migrate up and down the x and y axis first, assuming that I care about that part of my slope field. So let's go along the t-axis as well. What happens if t increases? When t increases, looking at my differential equation, I have a coefficient of -1 on my value of t. So that means that my slope is going to decrease as I move to the right, and it should increase as I move to the left. All right, so now let's think about what happens as I kind of move up and to the right. Well, if I move up and to the right, then my slope should be constant, or it should not change, because, like, let's say I go to the point 1, 1, then I have increased x by 1 and I have increased t by 1. Those things cancel out. So along this diagonal, in both directions, I should have a slope of 1. All right, so what other gaps do I have to fill in? Let's do the rest of quadrant 1. What if I go up to 1, 2? Well, we already discussed that if I increase by x, my slope increases. What about 2, 1? Well, if we increase by t, our slope decreases. And by the same token, if we go left, our slope increases. So really trying to point out that these are getting steeper and steeper. And if x goes up, this gets even steeper. So basically, what I'm seeing here, like I said, the point of a slope field, or what I think is the most significant thing, the biggest reason for doing a slope field, is getting an overall sense of how your differential equation responds as your variables vary. And in this case, it looks like, all right, upward and to the left gives me larger values for x prime, which should mean that lower and to the right should give me, those should be associated with decreases. Those should be associated with negative values of x prime. So we've already said that moving to the right gives us negative slopes, and moving down makes our slopes decrease. Moving left changes our slopes for the greater, as does moving up. So I believe that is, again, hand drawn. I didn't bust out a calculator or anything. I mean, these are all integer values, but I believe this is a good representation of this slope field. All right, moving on to question 16. Each of the differential equations have several initial conditions specified. Sketch the solution curves that satisfy the initial conditions. Sketch your solutions. Okay, So before I dive in here, I'm going to rewrite this differential equation in a slightly different way because it can be factored a little bit. I'm going to factor this quadratic as x minus 1, x plus 1, x minus 2. And I am being asked to draw some solution curves. To do that, I should probably have a slope field. And I'm going to make my slope field a little wider. Like when I say wider, I mean I'm going to look at larger values of t and x. But here's the good news. As opposed to our last example, where dx dt depended on both x and t, this equation is what we call autonomous. What does that mean? Autonomous equations depend only on their dependent variable. So on the right-hand side of this differential equation, the only variable we see is x. So first thing I would like to do, and that's something I would strongly encourage, is this. Try to understand where your equation is going to be in equilibrium, or equivalently, where is dx dt going to equal 0? And if you think back to Calc 1, that means finding critical points or stationary points, whatever they were called for you. Usually a good place to start if you're trying to figure out where a function increases and decreases. So let's figure out where that happens first. So that's going to happen where this equation equals 0. And this is part of why I factored this as far as I could, because since these three factors multiplied together equal 0, then any one of these factors equaling 0 will make the entire equation equal 0. So from here, I can kind of look at this and see that my equilibrium points are going to happen at, let's draw some scales here. X equals -1. So my slope field at -1 is going to look like this. X minus 1 gives me an equilibrium condition at +1. So my slope field looks like this. And again, because this is an autonomous equation, I don't have to look. I don't have to be careful about what my slopes look like left and right, because the only variable that governs what these slopes look like is x. So x-axis, t-axis. All right, so now I have my equilibrium conditions. Now we should talk about or figure out what happens between basically everywhere else. And this is where we use the idea of phase lines. So let's draw a phase line. Basically, a phase line is a condensed version of a slope field. Basically, a slope field is this two-dimensional arrangement, two-dimensional diagram. A phase line is one dimension. I'm only looking at x values. So I know I have equilibrium at -1, 1, and 2. To figure out what's going on elsewhere, I can test points basically on these little subintervals. So let's start from the bottom and go up. What happens for values of x that are less than -1? So for example, -2. So let's plug in -2 for these values. And I'm not really going to, I don't really care what the value is aside from whether it's negative or positive. So -2 minus 1 is negative. -2 plus 1 is negative. -2 minus 2 is negative. So if I multiply three negatives together, that's negative. All right, what about between -1 and 1? 0 is always convenient to use. If I plug in 0 for these x's, I get a negative times a positive times a negative. So it's an even number of negatives, so that's positive. Between 1 and 2, so like say 1.5, that gives me a positive times a positive times a negative. So between these 2 points, I have negative. And finally, let's choose 3. Anything bigger than 2 is fine. 2 minus 1 is positive. 2 plus 1 is positive. No, sorry, 2 doesn't work. I need strictly bigger than 2. 3 minus 1 is positive. 3 plus 1 is positive. 3 minus 2 is positive. So 3 positive factors all multiplied together gives me positive. All right, so now I'm going to bring this phase line arrangement back to my diagram, or my slope field. So below my least equilibrium point, I'm going to have slopes that look like this. And according to my phase line, the decrease should get more significant. The further I get away from that line. What happens between -1 and 1? I should have increases. And between 1 and 2, I should have decreases. So as I'm drawing this, I want to point out that all of these slopes I'm drawing should be identical, but because I'm hand drawing it, I realize they probably don't look that way. And finally, for values greater than 2, I should have increase. Okay, so now we got a slope field. So what? We are given some initial conditions and asked to give basically the rest of the curve. So if x of 0 equals 1, so let's make a point there. If x of 0 equals 1, we are on an equilibrium condition. That means that we are not going to have any variation. So that solution is going to look like this. You're going to have y equals 1, or x equals 1 is the solution. All right, if x of 0 equals 0. So if this curve passes the origin, let's follow it to the right first. First thing we're told is that if we're going to the right, we have increase. So this is going to go, oops, sorry. This is going to go toward our equilibrium condition, but the closer we get to it, the more it's going to flatten out. What about when we go left? Well, if we increase going to the right, that means that as we go to the left, we're going to have a decrease. And we're going to approach this equilibrium value at -1. All right, finally, x of 0 equals -1. So this is same kind of situation as the first one. If our initial point exists on this equilibrium line, we're not going to have any variation. So our basically, our three different solutions, of the three solutions we have here, 2 of them are going to be horizontal lines. The middle one we graphed, that goes through the origin, x of 0 equals 0, that one's going to be a curve. All right, moving on to question 22. Consider the differential equation y prime equals f of y. I must have had a reason for making that small, but it doesn't make sense to me now. Okay, so what is in this graph is essentially y prime. F of y is y prime. Draw the phase line for each equation, or this equation, and classify each equilibrium solution as a sink, source, or node. Okay, so basically we're given a graph that shows the value of the derivative. So again, sometimes I tell you what my personal preferences are for me. I think I would go so far in this case to encourage you to start with equilibrium. So what we're looking for is this. We're trying to characterize dy dt. And it's probably easiest to characterize it. When I say characterize it, I want to know where it increases where it decreases. And that's going to kind of that's going to tell me what kind of equilibrium points I have. But I should probably figure out where my equilibrium points are first. So if I am looking at a graph of my derivative, where is equilibrium going to happen? Well, by definition of what equilibrium is, that is where dy dt or y prime is equal to 0. So where does that happen? That happens at these two values. Let's say positive and negative 2.2. So this is y, negative 2.2, positive 2.2, and I have equilibrium at those points. Good, so I've identified equilibrium. Now I want to figure out what kind of equilibrium do I have at those points. So kind of like with the last example, I want to know what's happening at every part of like, basically, okay, let me back up. I'm going to let my equilibrium points basically divide all the real numbers up into 3 sections. The numbers that are less than negative 2.2, the numbers that are greater than positive 2.2, and the numbers that are strictly between negative 2.2 and positive 2.2. So let's start from the bottom again. If I have a y value that's less than negative 2.2, what's the value of dy dt? So anywhere left of that first equilibrium point, it looks like I have negative value for f of y, which implies a decrease. What about values between those two? Let's see where it crosses the y-axis. Those are positive values. And then finally, what happens to the right of 2.2? So for y values that are greater than 2.2, I have a decrease again. So make that clear. Extend this a bit more. So what does that tell us? So now that I know increase and decrease everywhere, I should be able to tell you what kind of equilibrium points I have. So again, starting from the bottom, negative 2.2, what's happening for values below that y value? If I have a y value of say negative 3, then the y values are going to continue to decrease. If I have a y value of, let's say, negative 2, then my values are going to increase away from negative 2.2. So no matter on which side, regardless of whether I'm above negative 2.2 or below negative 2.2, y is going to trend away. So that is the definition of a source, or equivalently, a point that is unstable. Our other point, I believe, has the exact opposite behavior. No matter on which side of 2.2 we deviate from, we will trend back to 2.2. So these points are called sinks, and these are stable. So when we talk about the stability of an equilibrium point, one thing I want to point out is that we're not really talking about the equilibrium point itself. Because if you are at the equilibrium value, nothing's going to change. dy dt is going to be 0. Your value of y is going to hold steady there. So when we talk about equilibrium, we're really talking about what happens near these points. Will you return to that value? Will you return to the equilibrium value, or will you run away from it? So for sources, you'll run away from it. For sinks, you will trend toward it. So in this case, we have one sink, one source, and then the third option is when we're stable from one direction and unstable from the other. Those are called nodes, but we don't have that in this case.